I think we can pretty well finish up on this video here. Okay, so let's see how we do. This is page number 4, it appears. Okay, so page number 4. So I think that's okay for major and minor losses, right? Again, the major losses depend on this Darcy friction factor. This Darcy friction factor, as we said back here, Darcy friction factor is a function of the Reynolds number and epsilon over d. Now, epsilon over d really becomes a factor if I'm dealing with turbulent flow. If I'm dealing with laminar flow, the epsilon over d really kind of falls off. The Reynolds number is what takes over. In both cases, whether it's turbulent or laminar, the Reynolds number is a contributing factor. Epsilon over d plays a bigger role if I'm dealing with turbulent flow, and that shows up in one of these 3 methods. Okay, so be comfortable with at least one of those 3 methods, probably a couple, and use them to kind of check against each other. Okay, the Colebrook is actually pretty easy to use at this point. If you've used it before, it's actually not too bad. You can pretty well program it in your calculator and have it preset, and that's okay. I don't mind that. Okay. Anyway, if you have questions about that, let me know. In general, looks like you guys did okay on exam 3, so we'll go from there. I'm working on grading those. I'll try to get those to you in the next day or so. Okay. Drag forces. Now, against my better judgment, as you can see, this is topic number 7, and it's like, Steve, there's no way we can work 7 or 8 problems. I know. I think this is one, a lot of these other topics I can work together into single problems, or combine a few of the smaller ones into another problem. This one, it either has to be a problem on its own, or I just cut it, and we're just going to cut it. So you guys get lucky this semester. Right, your final exam is not going to look like my typical final exam, by the way. Right, so if you talk to somebody that's taken my class before, your final is going to look different, A, because it's online, and B, we just didn't have the number of days this semester because we lost some. Okay, so I'm not going to put drag forces on the final exam. Yay, for whatever that's worth. Right, make sure you understand how that works. That's going to be expected of you in the next class, but it's probably not as critical as some of this other stuff. I'm going to go ahead and put open channel flow on there, though. If you've looked at it, that's a pretty straightforward topic. Again, this is internal flow, not completely filled conduits. And all I'm going to put on here is some use of the Manning equation. All right, so I'm not going to go real in-depth here. It's going to be pretty straightforward. It assumes uniform flow. If you don't know what that means, watch the video where I talk about open channel flow. If I have uniform flow, then approximating flow characteristics for an open channel is pretty simple. What we can do is we can say, well, the average speed of that flow is equal to dimension correction factor, A, divided by what we call the Manning coefficient, N, multiplied by a quantity we call the hydraulic radius that describes the geometry of the conduit or the channel. That gets raised to the 2/3 power. Right? So that gets squared and then third rooted. Multiplied by what we call the bottom slope, the square root of the bottom slope. So the bottom slope is a dimensionless quantity. Okay? The hydraulic radius, which is very similar to the hydraulic diameter we saw in Chapter 8, that is the cross-sectional area of the channel, the cross-sectional area of the fluid, divided by what we call the wetted perimeter, the total length that the fluid is in contact with. Not the perimeter of the duct or conduit, because the fluid, the whole point of open channel is the fluid is not in contact with the entire conduit. It's not completely filled. So some of the conduit is dry, some of the conduit is not wetted. The wetted perimeter is the total length of conduit that is in contact with the fluid, and this is the cross-sectional area of the fluid. The ratio there has dimensions of length. This is length squared over length, so this has dimensions of length. This gets raised to the 2/3 power, and this A has units to correct for this 2/3 length dimension that comes out of this here. Okay, so look at the homework problems. Hopefully that'll make some more sense. S naught is what we call the bottom slope. And this basically represents the change in elevation for the conduit per unit length. Right? That's the rise over run, if you will, for this conduit. That's again, if it's in an open channel, I cannot apply a back pressure. So the only thing that drives this fluid moving downstream is the change in elevation. The bottom slope is a measure of that change in elevation. That's delta Z over L. Okay. Now, how does this help us? Well, what this does is instead of having to figure out the energy loss for this open channel and then solving for the unknown speed based on the other characteristics, this gentleman by the name of Manning came along and said, hey, we can quantify this a slightly different way. These are the only driving factors. Well, and also the channel itself. So this N is what we call the Manning coefficient. Right? And it basically takes the place of the roughness of the conduit. Right? So this is analogous to this roughness. The rougher the conduit, the higher the Manning coefficient. Okay? So what we're saying in open channel is the only thing that really drives the flow, that's going to increase the flow, is going to be the rate at which the flow moves downhill, the geometry of the conduit, and how rough the conduit is. And these are the factors that are going to drive this. This is a constant value. This is just a correction factor. The other three are parameters, depending on the channel I'm dealing with. Okay? So these are pretty simple. If you wanted to know the volumetric flow rate, that's just equal to the cross-sectional area times the speed, as it always has been. Okay? Okay? So, I'm trying to think if there's anything else, guys. I think that's got us. That's what I've got on my note sheet here. I've gone through everything I want to talk about. Let me know what's not clear. And again, I'll put out details and logistics and good detailed information about how the exam is going to work. Take your time, read through that, and then go take the exam. Okay? Let me know if you have questions. I'm not going to tell you a date because I don't remember it off the top of my head. I got to look at it. It'll either be available either on Monday or Wednesday, whatever day the final was scheduled to be. That's the day that I'll make the exam available on Canvas, and we'll go from there. Okay? All right, guys. Yeah, I can't think of anything else. So ask me when you have questions. Send me an email. Find me in the chat room. Or send me an email and say, hey, Steve, can you meet me in the chat room at this time? Or, hey, Steve, can we do a Zoom call at this particular time? Or we can find some communication method, and I'll try to help you guys out any way I can. Happy to do that. Just let me know what it looks like. All right, guys. Stay safe. Stay healthy. Good luck on all your finals. See you guys soon. Bye-bye. Loud Popper.